Hello! Assuming you have been following along up to this point with building your view projection matrices for a directional light, you should have the tools needed to complete the task, but there is a problem with our current solution. The problem is often referred to as Shimmering Shadows. Let's watch a video to see the Shimmering Shadow artifacts in our engine. Any jokes about how we are watching a video of a video and the movie Inception are not appropriate. Hopefully, you can see that whenever the camera is being moved, the shadows wiggle or shimmer. This is something that is definitely worth some time to fix. This wiggling or shimmering error that we are seeing is caused by changes being made each frame to both the size of our projection and the translation of our view matrix. Both of these actions will cause subtle changes to where our shadow pixels fall frame to frame. First, we will fix the issue of changing the size of our projection. The reason we would be changing the size of our projection each frame is to account for the changing orientation of the camera's frustum. The most common way to fix the issue as it relates to changing the projection size is to not change the projection size. To be able to do this, we will need to use a slightly larger projection, one that would fit any orientation of the camera's frustum. By basing our projection box's size on the size of a sphere wrapped around the camera frustum, we will get a projection that will always fit and does not need to be changed each frame. This fix does come with a cost, as we are not getting the tightest fitting projection possible anymore, so we will lose some shadow resolution quality. Fixing the issue with the view matrix will be a bit more involved than the projection was. The issue with the view matrix translation is that we are very likely to move the matrix in a manner that results with us trying to write to non-existing partial texel locations. As an example, if our shadow map texture was 50 texels wide, we might try to write to a texel that is 13.3456 units to the right. There is no texel 13.3456 though, so we will end up at 13. The next frame, we might make a slight change, and maybe the same part of the shadow ends up in texel 14. Subtle changes in location can then cause these texels to dance around. To fix this, we will limit the movement of our light's view matrix to be in whole texel units. To limit our view matrix translation to whole texels, we will actually determine how much error, if any, we currently have in our view matrix, then translate backwards that error amount to remove it. To calculate the error, we will put a point in space first into our light's view projection space, then into actual texel space. This texel space representation will tell us what texel would store the given location and how much error we have. Here, we can see the steps for calculating this error amount. The WS point, or world space point, variable is any point in space. all points will give the same amount of error. In step 3, you are told to calculate the fractional part of the TS point.xy values. We leave figuring out how to do this to the student. The lab document will have a slightly harder solution than what is actually required. As a hint, if we wanted to find the whole number part instead of the fractional part, we could just typecast the TS point float as an integer. Once we have found the amount of error, we will need to convert it back to our light's view projection space before we can apply changes based on it. After that, we can either translate negative the error amount or translate 1 minus the error amount to limit our movement to whole texels. Shimmering shadow artifacts tend to be very noticeable by an end user and should be fixed where possible. This issue only happens if we are changing our view and projection matrices each frame. If you can avoid moving and changing them, then you can also avoid solving this problem. But that is not going to be the common case. In the next video, we will discuss building and using the view projection matrices for a point light.